In this video, we'll finally write down the formal definition of continuity, and we can prove some of the properties that it has that we may have just taken for granted in a calculus course, such as the fact that sums or products or compositions of continuous functions are still continuous. And instead of defining what it means for a function to be continuous overall, we focus on continuity at a point so that we can make a more concrete definition. And it'll end up looking really similar to our epsilon delta definition of limits. We say that a function f from a to r is continuous at a point c in a if, for all epsilon greater than 0, there exists a delta greater than 0, such that for all x in a with the absolute value of x minus c less than delta, the absolute value of f of x minus f of c is less than epsilon. So there's two key differences between this definition and the definition of the limit at a point. The first is that instead of comparing the distance of the output to some limit L, we're comparing the distance of nearby outputs to the function value itself. And the second difference is that we don't have that greater than 0 requirement on the distance between x and the input. So the picture for continuity is basically the same, where we can picture a nice smooth function, in which case for any epsilon window we place around the output, f of c, there will be a corresponding delta window that we could place around the input c, such that that entire delta window maps within the epsilon window. But this example that we looked at last time wouldn't be continuous at c, even though the limit exists at c, because the limit only cares about the surrounding points, whereas the definition of continuity needs that the surrounding points have similar outputs to the function value at c itself. So why not just take the definition we probably see in a calculus course, which is that a function is continuous at a point c in its domain if the limit as x approaches c of f of x exists and equals f of c. These two are roughly equivalent. The only distinction is that our definition of continuity actually allows isolated points to be considered continuous by default. So if c is a limit point of the domain A, then these two would be equivalent. And we have one more way to think about continuity, in addition to this epsilon delta window version, and then this equaling the limit of the function version. We could have a sequential characterization, analogous to how we had a sequential characterization to the definition of a limit. So we could say that a function f from a to r is continuous at a point c if, for every sequence xn converging to c that lives in a, the corresponding sequence f of xn converges to f of c. And again, this looks really similar to our sequential characterization of limits. It's just missing the hypothesis that the terms need not be equal to c. The proof that this is equivalent to our definition is fairly immediate. If c is a limit point of a, then this sequential statement is basically the same as the limit existing and equaling f of c. And if c is not a limit point of a, then by definition, there's no sequence of inputs xn that live in the domain A that converge to c. So c is continuous by default. Let's prove that combining continuous functions preserves continuity. So we could state the algebraic continuity theorem. So let's assume that f and g from a to r are continuous at some point c in a. Then kf of x is continuous at c for all k in r. F of x plus g of x is continuous at c. F of x times g of x is continuous at c. And f of x divided by g of x is continuous at c, provided the quotient is defined. So this is basically just another one of our algebraic limit theorem type statements saying that continuity is preserved under scalar multiplication, addition, multiplication, and division. The proof of this breaks down into just two simple cases. If c is an isolated point of a, then any function defined on a is continuous at c by default. So all of these functions would be continuous at c. And if c is not an isolated point, meaning it's a limit point, then because of the continuity of f, the limit as x approaches c of f of x equals f of c. And so by the algebraic limit theorem for functional limits, we get that the limit as x approaches c of kf of x equals kf of c, etc., which correspond to these four functions being continuous at c. This implies that polynomials are continuous on their entire domain, because the identity function f of x equals x is continuous, and polynomials are all formed by just multiplying this function by itself, or scaling this function, or adding copies of those scaled multiples. And then we also get that any rational function, any ratio of two polynomials, is continuous on its entire domain. We can also prove that compositions of continuous functions are continuous. Let f from b to r and g from a to b be such that g is continuous at some c in a, and f is continuous at the corresponding g of c in b. Then the function f composed with g from a to r is continuous at c. For the proof of this, let's use the sequential characterization of continuity. So let xn be a sequence in A that converges to C. By the continuity of g at C, we know that the sequence g of xn converges to g of C. And now by the continuity of f at g of C, we know that the sequence f of g of xn converges to f of g of C. Since we started with an arbitrary sequence, it holds for every sequence, and so the function f composed with g is continuous at C. We demonstrated last video that the limit as x approaches 0 of cosine 1 over x does not exist, because we could construct two different sequences of inputs which have corresponding output sequences converging to different limits. Since 0 was a limit point of that domain, that automatically means the function cosine 1 over x is not continuous at 0. What if we modify the function to x cosine 1 over x if x is non-zero, and then 0 if x is equal to 0? Is this continuous at 0? We could again draw its graph, and it has a similar increasing oscillation as we approach 0 on the x-axis, except now instead of having a constant amplitude, it's oscillating up toward the line y equals x and y equals negative x. So what do you think? Is this continuous at 0? The answer is yes. Let's justify it from the definition. So we consider an arbitrary epsilon window around 0 on the y-axis, the output of the function. And we need to produce a delta window around 0 whose inputs will map within this epsilon window. We can use the fact that the cosine function always oscillates between -1 and 1. So the absolute value of cosine 1 over x is always less than or equal to 1, which means the absolute value of our function, x cosine 1 over x, is less than or equal to the absolute value of x. So we can simply choose delta equal to epsilon, and observe that for any absolute value of x less than this delta, the absolute value of our function, x cosine 1 over x, is less than or equal to absolute value of x is less than delta equals epsilon. So this function is continuous at 0. So far we've asked the question, what preserves continuity? What operations can we apply to functions such that the result is continuous? But we could flip that on its head, and we could ask, what does continuity preserve? In other words, what qualities about a set may be retained by passing it through a continuous function? Is the continuous image of an open set still open? Is the continuous image of a closed set still closed? What about a compact set? It's always good to ask probing questions, even if it seems like the answer is going to be no, because it presents the natural challenge of constructing a counterexample, which is a useful skill. So for that first question, a counterexample that comes to mind is f of x equals 3. The domain here is the real numbers, which is an open set, and yet the range of the function is the singleton set containing 3, which is not open. What about that second question? Is the continuous image of a closed set still closed? This one's slightly trickier to come up with a counterexample, because if you just start considering simple functions, like the trivial function I defined earlier, or maybe the function f of x equals 4x, which just scales everything by a factor of 4, then the property of being closed does seem to be preserved. But let's consider maybe the function f of x equals 1 over x. And we still have to choose the input set carefully to construct a counterexample. If we just take the closed interval 1 to 2, that still maps to a closed interval. But we don't need a closed interval, just any closed set. So let's take the set of all numbers greater than or equal to 1, the interval from 1 to infinity. If we pass this through the function 1 over x, then we get the half-open interval 0 to 1, not containing 0, which is not a closed set. Although the fact that I needed to take a set that was headed off toward infinity to construct a counterexample is suggestive of the fact that maybe this will be true with compact sets, because a set being compact is equivalent to being closed and bounded, so we couldn't use the same counterexample. Let's state this as a theorem. Let f be a function defined on a compact domain A that's continuous on its entire domain. Then the image f of A is compact. Since we need to show that some set is compact, we'll need to use one of our 3 characterizations of compactness. Let's use that first one that we took as its definition, that any sequence in the set has a subsequence converging to a limit in the set. Since that's a for all sequences, let's take an arbitrary sequence. So let y sub n be a sequence contained in f sub a. Our strategy for finding the desired subsequence will be to find the corresponding input values back in the set A, which we know to be compact, use the compactness of A, and then translate back. So we could say, for each n, let xn be such that f of xn equals yn. And this isn't guaranteed to be a unique choice of xn, but we're guaranteed that it exists because y is contained in f of a, the image of a. Since A is compact, there exists a sequence x sub nk converging to a limit x in A. By the continuity of f, the sequence y sub nk converges to f of x in f of A. Therefore, f of A is compact. In the next video, we'll discuss the extreme value theorem, the intermediate value theorem, and uniform continuity.